In this video, we are going to be discussing improper integrals. However, unlike the previous video, where we discussed them where the limits of integration were infinite, in this case, we will be discussing integrals that are across an interval that has an infinite discontinuity at one side or the other. For example, consider the function 1 over x, which we used to talk about the previous situation with improper integrals. But instead of this time of going from 1 to infinity, in this case, we would be looking at the region to the left of 1, the region from 0 to 1. Now, unlike integrals where the limits of integration are infinite, those are obviously improper. Integrals that go across an interval with an infinite discontinuity are not so obvious. There is nothing immediately apparent in this integral that suggests that it would be improper. We can only determine that based on our knowledge of the function, specifically thinking of its domain, which it may help to have a picture of the graph in our heads if it's simple enough, such as 1 over x, or may require actually producing the graph using perhaps a graphing calculator. The approach to these is very much the same, however. The idea is that we have a limit of integration that, if we attempt to apply the fundamental theorem of calculus to it, that limit of integration will cause a problem when we try to evaluate the antiderivative. The way we get around that, of course, is to replace the troublesome limit of integration with a variable and then use a limit. So in a case such as this, we would replace the lower limit of integration, 0, with a, and then precede the integral with a limit as a approaches 0 from the right. Please note that we will need to be specific about which side we are approaching from, because we still cannot actually integrate across an infinite discontinuity or even at an infinite discontinuity. We can only approach it from the relevant side. Suppose, however, we were looking at an integral that was on the left side of the discontinuity. For example, suppose it was from -2 to 0 of 1 over x dx. In this case, we would be in quadrant 3. In this case, we would have to replace the upper limit of integration with a variable, and our limit would be as b approaches 0 from the left. There is always the possibility that our interval begins on one side of an infinite discontinuity and ends on the other side of it. In a situation such as this, even though neither of the limits themselves is an issue, we do have an x value on the interior of the interval that would cause an issue. In this case, we will have to split the interval at the location of the infinite discontinuity, and then handle each separate integral in the ways outlined above. These can be the most difficult to catch. Sometimes the limit of integration that is the problem is fairly obvious, such as the zeros in the first two examples here. Because 1 over 0 is a problem, obviously there is a discontinuity there. However, in the third integral here, from -2 to 1, it is not immediately obvious that there would be a problem unless we are observing this very carefully. For our first example, let us take the first integral we were looking at, from 0 to 1 of 1 over x dx, which of course is improper at the left limit of integration. So we will start by replacing that with an a and have the limit as a approaches 0 from the right. Our three steps are as before. First, we find the antiderivative. Very simple and straightforward in this case. The natural logarithm of the absolute value of x. Because we happen to know that we are on an interval from 0 to positive 1, that means we can get away with dropping the absolute value. As long as we remain on positive x values, then we have no reason for the absolute value. Our second step then is, of course, to apply the fundamental theorem of calculus to the integral from a to 1 of 1 over x dx, which would be the antiderivative, the natural log of x, evaluated at 1 minus the evaluation at a. Where, of course, the natural logarithm of 1 is 0, and thus we are left with negative natural logarithm of a. Our last step, then, is, of course, to evaluate the limit. So we have negative natural logarithm of something that is approaching 0 from the right. Approaching from the right is relevant because the natural logarithm is only defined for positive x values, so we must approach from the right. But as we do so, the natural logarithm drops towards negative infinity. So we have the opposite of something that is approaching negative infinity. Therefore, this is approaching positive infinity. And thus, this integral diverges. This should not be surprising because the interval, the physical region of the graph, is symmetric to what we saw in the previous video when we integrated from 1 to infinity. It does include an extra square from 0 to 1, but aside from that, the region in question is symmetric and identical. So this region is actually, because of that extra square, ever so slightly bigger. If the example from 1 to infinity diverges, this being slightly larger must also diverge. Let's consider an example where the integral converges. In this case, we will look at an integral from 0 to 1 of 1 over the cube root of x dx. This has a similar region to the 1 over x. However, as we saw in the previous video, it's not just a matter of the fact that the region is unbounded or even that it is similar in shape, because the rate at which the graph is approaching its asymptote, is relevant to whether the integral will converge or diverge. So, like before, this has an infinite discontinuity at x equals 0, and so we need to replace the lower limit with a variable a. At this point, I will also recognize that in order to do the antiderivative, we're going to need to rewrite 1 over x to the cube root of x as x to the negative 1/3. This will, of course, enable us to use the power rule, which will result in x to the positive 2/3 over 2/3, which can be rewritten as 3/2 times x to the 2/3. The plus c can, of course, be omitted since we are about to do the fundamental theorem of calculus. We may choose to rewrite the x to the 2/3 into a radical form, but until I have reason to do so, I will leave it in its fraction exponent form. Our integral is from a to 1. So we have our antiderivative, 3/2 x to the 2/3, evaluated at 1 minus the evaluation at a. Of course, 1 to any power is itself, so our first term is simply 3/2. And at this point, we may find it helpful to factor out the common 3/2. It may just make our lives a little bit easier when we have to evaluate the limit in our next step. But it is, of course, not necessary. Our final step then is to evaluate the limit. So our original integral was rewritten as the limit as a approaches 0 from the right of the integral from a to 1. Which we now know to be equivalent to 3/2 times 1 minus a to the 2/3. The 3/2 is a constant multiple, and thus it is unaffected by the limit, and is simply present as a constant multiple of the answer. What we have then is the 1, which is also unaffected by the limit, and then we have the a, which is a value approaching 0 from the right, raised to the 2/3 power. As we approach 0, but always positive, a positive number approaching 0 raised to the 2/3 power will simply get smaller and smaller and smaller. This entire term will approach 0. Thus, in the parentheses, this entire expression will approach 1, and thus the entire integral will approach the value 3/2. Thus we can say the integral from 0 to 1 of 1 over the cube root of x dx converges to 3/2. Again, it is commonly simply said that the integral is equal to 3/2. However, because the region is unbounded, it never actually reaches an area of 3/2. And while by convention it is okay to say that it equals 3/2, for things that we will see later in this course, it is more appropriate to say that it converges to 3/2 than to say that it is equal to 3/2. Let us consider another example. In this case, we are going to look at an example of an interval where the infinite discontinuity is on the interior of the interval. The interval from -1 to +2 of 1 over x cubed dx. Fortunately, this function, its infinite discontinuity, is relatively obvious to find at x equals 0. Thus, we have to split the integral into two pieces. Because we cannot integrate across the infinite discontinuity, we can only integrate up to it. And then on the other side, we can only integrate after it. We cannot actually integrate at or across the infinite discontinuity. And this is where our limits come in. The limit as b approaches 0 from the left of the integral from -1 to b. So we can allow that upper limit of integration to approach 0, but not actually reach it. In the case of the second integral, we would have a approaching 0 from the right, so that our lower limit of integration can approach the infinite discontinuity, but not actually reach it. We saw an example akin to this in the previous video, where we had to split an integral that went from -infinity to +infinity into two pieces. And fortunately, since it is still the same integrand, they both have the same antiderivative, which means we only have to do that once. The antiderivative here is simple enough. We start by writing 1 over x cubed as x to the -3, enabling us to use the power rule, which gives us x to the -2 over -2, which is -1 over 2x squared. Now, the reason I chose to rewrite this negative exponent into the denominator with a positive exponent, as opposed to the previous example where I left the fraction exponent as a fraction, is that in this case, when we again have to evaluate our limits, it will be easier to understand what's going on with a positive exponent that is in the denominator rather than with a negative exponent. A fraction exponent isn't really any harder than dealing with a radical in terms of this, but a positive exponent is certainly much easier than a negative exponent. We now need to do the fundamental theorem of calculus for each of our integrals. So starting with the first one, from -1 to b, this gives us -1 over 2x squared evaluated at b minus the evaluation at -1, which gives us -1 over 2b squared minus -1 over 2 times -1 squared. -1 squared is, of course, simply 1, leaving us with 1/2, where the subtraction and the negative cancel out, leaving us with -1 over 2b squared plus 1/2. For the other integral, from a to 2 of 1 over x cubed dx, we again have our antiderivative, -1 over 2x squared, this time evaluated at 2 minus the evaluation at a. So negative 1 over 2 times 2 squared minus negative 1 over 2a squared, which simplifies to negative 1/8 plus 1 over 2a squared. Now, an important thing to realize here is while the original integral has been split into two, each separate integral is being evaluated separately. So when we go to the limits, we need to consider what's going on with each one separately, even if we write them together into the same thing. That is to say, even if we are writing it as, even if we are writing it as two limits of two integrals, we need to consider each integral separately, because while the original was written as a single integral, it cannot possibly be considered a single thing. It has to be separated into the two. So while evaluating this, while we may write them next to each other, we need to consider each limit separately. So our first is going to be the limit as b approaches 0 from the left of negative 1 over 2b squared plus 1/2. And then our second limit is going to be the limit as a approaches 0 from the right of negative 1/8 plus 1 over 2a squared. Now again, considering them separately, we have negative 1 over 2 times something that is approaching 0 squared. As b approaches 0, b squared also approaches 0, and thus the denominator of the first fraction approaches 0. This first term in parentheses here is going to approach negative infinity. That means that this integral diverges without even approaching the other limit, without even dealing with it. We already know that this particular integral diverges. Therefore, the entire original integral must diverge, regardless of what goes on with the second integral and the second limit. If one part of this diverges, the entire thing diverges. Now, if we wish to approach the other part of this, we have negative 1/8 plus 1 over 2 times a squared, where a is approaching 0. And we have the same situation here, where this term is going to end up approaching infinity. Please do not be fooled by the fact that one of them is approaching negative infinity while the other is approaching positive infinity. We know that to be an indeterminate form. That does not necessarily cancel out to 0. What this shows us is that this second integral from a to 2, from 0 to 2 of 1 over x cubed dx also diverges. Thus, the original integral from negative 1 to 2 of 1 over x cubed dx also diverges. It is important to note that when we split an interval into two integrals, that if either one of them diverges, then the original integral also diverges. We're going to look at one further example, an example of a doubly improper integral, meaning that it is going to be improper for two reasons. One of those reasons is immediately apparent. The upper limit of integration is infinity. That is an instant indication that we are dealing with an improper integral. Less obvious is what's going on at the other limit of integration, or perhaps somewhere in the middle. This function would have infinite discontinuities wherever the denominator is 0, which means at -1, which is not between 0 and infinity, and therefore is not a consideration, but also at 0, where the square root of x would approach 0. So this is improper at both endpoints. And as such, we're going to need to split the integral somewhere in between them. It doesn't matter where. We could split it at 10 or 100 or at 12.6 if we chose, but we might as well choose a value that's easy to work with, such as 1. So we can integrate this from 0 to 1, which will allow us to deal with the lower limit of integration as our improper limit. And then separately from 1 to infinity, which will allow us to deal with the infinity as our improper limit. Each of these will, of course, need to have its limit of integration that is causing the problem replaced by a variable. But once again, we are fortunate enough that in splitting this integral into two pieces, we do have the same integrand. And as such, that means we only really need to do the antiderivative the one time. And that, of course, is our first step. The antiderivative first. This is not an immediately apparent integrand that fits one of our integration rules that we have. It is not immediately apparent. It does have some reminiscence to some of the integrals that result in the inverse trigonometric functions, or even perhaps the inverse hyperbolic functions, except for the fact that it doesn't have a sum or difference of squares. Or it does if we are sneaky. Now we'll deal with that square root of x out there in a moment. That does perhaps make us think, because of the extra factor out there, it might start to make you think of a arcsecant or an inverse hyperbolic secant, but it's not quite there. Let's start with establishing the sum or difference of cubes, or the sum of cubes in this case. The idea is that x plus 1, the x can be rewritten as the square root of x squared, where of course the 1 can be written as 1 squared. We can get away with replacing x with the square root of x squared because we are entirely dealing with positive numbers. Our interval is from 0 to positive infinity. And on that interval, the square root of x squared is exactly equal to x. This then, in turn, suggests a substitution that can be made, where u is equal to the square root of x, so that x plus 1 can be rewritten as u squared plus 1. Of course, then, that makes du equal to 1/2 times x to the negative 1/2 dx. And we do not have a 1/2 factor in our integrand, so we will have to multiply both sides by 2. I'm also going to return the x to the negative 1/2 to a radical form, which will move it to the denominator. And that covers our factor of 1 over the square root of x. So as it turns out, the 1 over the square root of x is part of the derivative of the inside function. Thus, our integral of 1 over the square root of x times x plus 1 dx can be rewritten as 2 times the integral of 1 over u squared plus 1 du, where the 1 over square root of x dx is replaced by the 2 du. And this neatly fits the form of the arctangent, where with one final step to return this to the original variable, we have as our antiderivative 2 times the arctangent of the square root of x. Our next step is to apply the fundamental theorem of calculus to each of our integrals. We will do them one at a time. We have first the integral from a to 1 of 1 over the square root of x times x plus 1 dx, which then would be equal to 2 times the arctangent of the square root of x evaluated at 1 minus the evaluation at a. Which gives us 2 times the arctangent of the square root of 1 minus 2 times the arctangent of the square root of a. And we can't do much with that second term, but the first term we can. The square root of 1 is, of course, 1. And the arctangent of 1 is pi over 4. So that when all is said and done, the first integral can be written as pi over 2 minus 2 times the arctangent of the square root of a. Our second integral then was from 1 to b, resulting in 2 times the arctangent of the square root of x evaluated at b minus the evaluation at 1, which gives us 2 times the arctangent of the square root of b minus 2 times the arctangent of the square root of 1, which, as we already saw earlier, 2 times the arctangent of the square root of 1 simplifies down to pi over 2. And now that we have applied the fundamental theorem of calculus, we are now ready to apply the limits. Remember that we need to be careful to pay attention to each separate integral, because if either one of them diverges, then the entire original integral will diverge. So we had made this into the limit as a approaches 0 from the right of the integral from a to 1 of our function plus the limit as b approaches infinity of the integral from 1 to b of our function. Where the definite integrals for each of these resulted in, for the first integral, pi over 2 minus 2 times the arctangent of the square root of a. And for the second integral, resulted in 2 times the arctangent of the square root of b minus pi over 2. Now again, let's not go nuts canceling out those pi over 2's just yet. We still need to treat each one separately to see if it diverges or converges. Because again, if either one of these diverges, the entire integral diverges. As far as the limit is concerned, since the pi over 2 is a constant, it remains pi over 2. So then we have minus 2 times the arctangent of the square root of something that is approaching 0 from the right. Again, approaching from the right is relevant because if we were not approaching from the right, if we were approaching from the left, then this would be completely undefined. But as long as we are approaching from the right, then the square root of something that is getting smaller and smaller also gets smaller and smaller. So that this becomes 2 times the arctangent of something that is thus approaching 0. But the arctangent of 0 is defined. The arctangent of 0 is 0. Thus, the first integral converges to pi over 2. As for the second limit, we now have 2 times the arctangent of the square root of something that is getting bigger and bigger and bigger. And of course, then, minus pi over 2 as a constant is not affected by the limit. The larger a value gets, the larger its square root gets. So that we have here 2 times the arctangent of something that is simply getting bigger and bigger and bigger. As the input value approaches infinity, the arctangent will approach pi over 2. Thus, the second integral also converges. To close ranks here, now that we know that both separate integrals converge, it is okay to begin combining like terms, which in this case simply means that the 2 pi over 2's here will cancel out and leave us simply with pi. Thus, the original integral from 0 to infinity of 1 over the square root of x times x plus 1 dx converges to pi.